So we are going to be, I'm sorry, recording this session. If anybody has any objections with the recording of the session, please say so now. And we're continuing with the set of problems that have to do with electric charge and Coulomb's law. And we were working on problem 10. This is an important problem because it kind of represents some things that we're going to be that we're going to be using a lot, and it kind of refreshes other things that you should have seen in statics and dynamics. I'm sorry, primarily the free body diagrams and how to represent forces and net forces or forces in equilibrium. And so I just want to refresh what this problem is about. And I need you guys to ask questions and for this problem to be clear before we move on to anything else. So first off, we've got three charges. I'm sorry, Q1, Q2, and Q3. Paulina, could you please refresh our memories? We had the value of the charges, right?
Yes, let me see. It is 4 times 10 to the 6.
So the charges, I'm going to just call it Q, are the same. It's Q1, the same as Q2, the same as Q3, and they're negative, correct. These are, Paulina, you said 4 times 10 to the
6.
To the 6. So it's minus 4 times 10 to the, it's to the minus 6, right, Paulina?
No, it's positive, but I don't know if that means that it's negative. In here, in the problem, it's positive. It just says that they are negatively charged.
Let me just check one thing here very quickly. That's a large, no, it is to the minus 6, Paulina.
Oh, I don't know if
yeah, this, I'm just going to show again. This is the problem. So it's 3 negatively charged spheres, each with a charge of 4 times 10 to the minus 6.
Oh, maybe when I put it in the PowerPoint,
yeah, now something important about this. I'm just mentioning, it's important to mention because of the following. Remember, we're going to be doing problems, and the problems have the analytical and the numbers and the formulas and all that, but I need you guys to understand what's behind that. And so why did I find it odd that the charge, let's see if you guys have been paying attention. Why did I find it odd that the charge would be 4 times 10 to the 6 rather than 4 times 10 to the minus 6? Why was that odd to me? And I asked to check that. Does somebody remember? This might be one of those weird think about it questions in the exam. Why did I find it odd for it to be multiplied to the 6 instead of the minus 6?
Because we are working with charges and it has to be like small numbers instead of
correct.
Different.
Correct. Very, very, very good. Very well. Well done, Marisa. Remember that when you participate, if possible, turn on your camera so you pop up and I see who you are, because I'm just showing the reduced version of the images. And so the charges that we have, we're going to be working with charges that the values of charges or coulombs are usually small values. So we're usually going to be working with micro coulombs, nano coulombs. So a charge of 1 coulomb is a huge charge. And so a charge of 4 times 10 to the 6, that would be an enormous charge, okay? That would be a huge charge. So that's why it was odd, okay? So remember one thing, because I'm gonna be copying, doing some screenshots of your presentations and your documents to put them in the PowerPoint so you have the problem solved. Remember to correct those things if they aren't stated correctly. And so all of the charges are the same. And so the charges are placed in an equilateral triangle, and each side is 0.2 meters. So we have this figure here. We know that each of the angles here is 60 degrees, and each of the charges are in one of the vertices of the triangle. Now they're asking us for the net force in each of the charges. Now, what we did here is that we placed ourselves here in Q2, and we did a free body diagram. I'm sorry. The purple arrows represent the forces, the electrical forces that are being applied or affected onto this charge. So if I'm here in Q2, what is the force that's being exerted between Q1 and Q2 if I'm here in Q2? Well, is it clear to everybody that it's a repulsion force? Okay, because both charges are negative. So the force is going outwards because if the two charges are negative and it's a repulsion force and I'm in Q2, Q2 is going to want to go away. So it's going outwards, and we're calling that F12. And F12 is going to be given by K Q1 Q2 divided by R squared. And then with Q3, it's the same situation. Q3 is negative also, so there's going to be a repulsion force, but the repulsion force is going to go along the line that joins Q2 and Q3, so there's going to be a force going downwards. And that force is going to have a 60-degree angle, and that's called force 3-2. That's K Q2 Q3 divided by R squared. Now, since the distances and the charges are the same, then the forces are going to be the same. The magnitude of those two forces are going to be the same, and I think we calculated that to be 3.59 newtons, okay? Questions up to this point? Remember, if you have any questions, please stop me. And so now, yes, please go ahead.
I have one comment. Like I'm getting pretty confused, but I mean, when we see a problem, like more like when you explain it, like I don't know how to explain. When we see examples, I'm going to get it, but right now I'm pretty confused. I just want to comment that.
Okay, let's see what because these are actually examples. Okay, so that's why I'm concerned a little bit about this. Please, what part? Let's get into that, because maybe you're not the only one who's confused, Rene. And this problem is important because this is kind of the type of problems that we need to understand. So let's stay on this problem. I don't have any issue with doing that, so we can get clear. So what part right now is the one that's generating confusion?
It's because I get the whole idea, like I get like the reasoning behind. I mean, I analyze it pretty good, and like I remember the statics course, but like on the forces, I get sometimes mixed up because of the charges. Like I don't know, like with the representation, I get confused in that part, like on the lines. I don't know if you understand me.
Okay. Yeah, so on if the force is going, in what direction the force is going, for example.
Like that.
So you understand
the cosine and sine that confuses.
Okay.
Also the cosine and the sine.
Okay. So the part of the confusion has to do with how do I know in what direction the force is going, and the other is what am I doing with the sines and cosines to represent the net force, right? Would that be fair to say that those are the confusion? Part of it?
Yeah, you could summarize it like that.
Okay. Let me do this. Okay. I am going to stop sharing this here for a moment. Let's see if this helps a little bit, because I think that actually I think that this is a good moment to kind of give a refresher about in general, the free body diagrams and how we represent forces and what are we going to do with that. Okay. Let's do this example. Okay. And please, Rene, I think Jose Carlos also participated, any of you. If any part of this that I'm going to explain, there's doubts or confusion, please let's stop and let's analyze it before we go back to the other problem. Okay. So let's assume that I've got, I have a, I have a free body diagram. Let's do this. Okay. Let's say that I have a ball here. Okay. This is physically a ball. Okay. Forget about electrons and stuff like that for a moment. It's a ball. Okay. And the ball has a couple of strings attached to it. Okay. Imagine that the ball that we're looking at, the ball is on the ground, and we're looking at the ball from the ball is on the floor. Okay, the ball is on the floor, and we're looking at the ball from up top. Are we okay up to that point? There's a ball on the floor.
Yes.
And let's say that we've got a couple of people here. We've got Rene. I'm going to try to draw you, Rene, but this is Rene. Okay. And over here we've got JC. How do we know that it's JC? Because JC has glasses. I'm terrible at drawing. Okay, JC has glasses. Okay. And let's say I'm going to tie a string to the ball. And this is two-dimensional, okay? This is two-dimensional. Let's not think about three-dimensional. It's two-dimensional. I'm going to tie a string to the ball. And I'm going to give one of the strings to Rene. And I'm going to give the other string to JC. Okay, are we okay up to that point?
Yeah.
Yes.
And then I ask both of them to pull. Okay, I ask both of them to pull. And I
Sure.
want to know, okay, questions? Yes?
He's on the other side, like we are standing in front of each other in the ball in the middle.
Yeah. Mm-hmm.
Okay.
But look at it this way. So that's the orientation you two have right now. Okay.
I'm asking because I want to know like if we're pulling to exactly opposite sides or if we're pulling like it looks like an L, right in the drawing. Do you know what I mean or no?
Another thing, don't complicate things more than they are. You're standing there and you're pulling outwards. Okay. Yeah. So don't start saying, well, what if I try to jump and what if I try to go around? No, don't. Let's not complicate things. Okay. So you guys are standing there and you JC are pulling this way and Rene is pulling this way. Okay. Directly outwards, in your case, JC, and Rene, you're pulling to the right, okay? Is that clear?
Yes.
Okay.
Yes.
And I want to know if Rene is pulling with a certain force and JC is pulling with a certain force, I'm going to say the following. I'm going to say that Rene is pulling with a force that I'm going to call FR. Okay. And JC is going to be pulling at a force that I'm going to call FJC. Are we okay up to that point?
Yes.
It's a force in newtons. Okay. Again, don't complicate things right now. Don't start. Well, what if Rene is stronger than JC and Rene? They're both pulling with the same force. But wait a minute, how are we measuring? They're both pulling with the same force. Okay. And I'm going to say that the forces are the same. I'm going to say that FR is the same as FJC right now. Both of them are pulling with the same force. I want to know in what direction the ball is going to go and with what force, with what total force it's going to be moving. Are we okay up to that point? I want to know in what direction the ball is going to go, and I want to know with what force it's going to be moving. By common sense, with what we're looking at the diagram, in what direction is the ball going to go? And anybody can just draw a line. In what direction do you think the ball is going to go?
Is it going to
Doesn't have
stay
to-
still? Because they're both pulling with the same force.
That's a good observation, and the answer is no, because the forces are the same, but there's an angle between them. Okay? The forces are the same, but there's an angle between them. Okay? The ball would stay exactly where it is in a situation where the forces were going against each other in the same direction. Okay? And by the way, think of it, forget about electrons or wherever. Again, you got a ball, René's pulling on one side and JC is pulling on the other with the same force. What's going to happen with the ball? Yep. Who drew that? Carmina. The ball is going to go down into the right. Is that clear to everybody?
Yes.
Yes.
Yes. Yes.
Is it clear that the ball is going to go down into the right? Now, do I know exactly in what direction? No, not yet. Do I know with what force? No, not yet. I need to find that. But is it clear that what Carmina drew, the ball is going to go this way? Okay, are we okay up to that point, everybody?
Yes.
Okay. How can I find the total force that's happening? Well, this is where the free body diagrams work. And I'm going to remember something about the free body diagrams. Free body diagrams establish a reference so I can calculate the forces. Okay. Now the reference should be according to the easiest way in which I can calculate them. Okay. So for example, I'm going to give a few examples. What if I say that the free diagram is going to go, because I got fuzzy brain and I'm not really thinking very much correctly, but I'm going to say that the free diagram is going to go like this. Why would that not be convenient? Anybody? Why would it not be, for example, René, why would it not be convenient for me to put the free body diagram like that?
Because it's not like strictly on the x-axis. It's like tilted.
Yeah, and even I can have it tilted, but ideally I would like some of the forces to go along the axis because that's going to make the calculations easier. So this isn't practical. So what am I going to do? I'm rather going to do a free body diagram like this. Okay. Is that better? Because at least one of the forces is aligned with one of the axes, right?
Yes.
Yes.
By the way, I could have also done this if I wanted to, because now I have another force aligned with the axis. But I mean, visually, I'm going to have to do this, so I'm not going to use that one. I'm going to do a free body diagram like this. Okay, please, everybody, are we okay up to this point?
Yes.
Yeah, I'm good.
Okay, good. Now, I want to know the total force. I want to know the total force that's being exerted. The total force. Write that down in green. And the total force, I want to know the magnitude, but I also want to know in what direction the force is going. And the direction is going to be given by some sort of angle here, okay? Now, how do I calculate the total force? Well, this is where we have to remember what we saw in statics and dynamics. And basically everything's based on Pythagoras. The total force is going to have two components. It's going to have an x component that I'm going to call fx. And it's going to have a y component. And there's going to be a resulting force that has both of these components, okay? Now, how do I calculate each of those components? Well, the x component of the total force is going to be the sum of all of the x components, or rather, I'm sorry, all of the forces that are going in x. And the y component is going to be the sum of all of the forces that are going in y. Are we okay up to that point? Is that part clear? Because that's this part about the sum of the forces, that's a very important part.
Yes, it's clear.
Yeah. Let's see, Rene, how are we doing there up to that point, and Jose Carlos and the rest also?
Yeah, I'm getting the whole idea.
So the total force is going to have an x component and a y component. And I need to find those. So how do I find those x and y components? Well, I need to look at the forces that are interacting here. So if I look along the x-axis, what forces do I have along the x-axis?
You have the positive force of me pulling the ball.
Correct.
And also the one of JC, because it also has the x component, right?
Yes, so that this is where the sines and the cosines start to become necessary.
Yeah, because for mine doesn't have an angle, and JC's has an angle on the x.
Exactly.
Okay.
So what's happening here is that so fx is going to have fr, which is your force, Rene, and your force is exactly along the x-axis, okay? But JC, you're pulling downwards, so you're contributing, since you're pulling at an angle, your force has an x component and a y component that contributes to the total force. And so we're going to have JC's x component of his force. And just for the purpose of this exercise, I'm going to say that the angle that JC's force has here, I'm just going to say that the angle is 60 degrees. Just for the purpose of this program. So the x component of the force that's going in diagonal, how do we calculate the x component? The x component is going to be the force multiplied by the cosine. So remember, if the angle is with respect to x, with regards to x, then x means cosine, y means sine. okay? If the angle is with regards to y, it's the other way around. X means sine, y means cosine. But right now I'm measuring the angle with regards to x, and so it's going to be JC's force.
It's gonna be cosine of 60
Cosine of 60, correct.
times the force. So you get, that's how you get the X force on the JC's pulling.
Yes, correct. And the total force in X is going to be your force, Rene, and the X component of JC's force. Okay. Now let's talk about the Y component. What is the Y component? How many forces are interacting with regards to the Y axis, meaning the vertical axis?
2.
Why 2? Let's look at Rene. Is Rene acting, is his force acting in the Y axis?
No, it's
No.
only
No.
one.
Only 1. Oh,
It's
yeah,
only
yeah.
JC's force.
Yeah, so Rene isn't acting on the y-axis. The only force that has a component in the y-axis is the one that has an inclination, which is JC's force. So the only force, and it's going down, right? So I'm going to take the reference just as a reference. If it's we need to have references for the signs and mostly for the angles. I'm going to say that right is positive, up is positive, down is negative, left is negative, just like a normal XY plane. So this would be minus FJC. And how do I calculate the Y component? What do I have to add?
The sine.
The sine of 60. Okay? And we do those calculations. The total force is going to be given by Pythagoras. It's always going to be given by Pythagoras. The total force is going to be the square root of the X force that I just calculated plus the Y force that I calculated. Okay. And how can I find the angle of this total force? Well, the angle is always going to be calculated using the inverse tangent. So the inverse tangent of Fy divided by Fx. It's going to be the tangent of of y divided by x. Okay. Is this clear? Or question?
Yes.
Because this is really the type of problems we're going to be solving. Now I might add a bunch of other forces, and the key part of this is to be able to calculate resulting forces, which are these total forces that we have there. Okay. Questions with this before we try to go back to the other problem?
No, I'm good.
Okay, is it a little bit, is
Questions?
this part of
We had the Fy and the Fx, right? And then how do we get it into the tangent? Because it was squared. I mean, how do we to the final answer?
I'm not sure I'm understanding the question, Juan Carlos, but Jose Carlos, I'm sorry.
Okay, I got lost in the last step when we had Ft equals the square root, and then we had that, and then what do we do after that?
Okay, let's do this just for the purpose of the exercise. Let's imagine that Fx, the total value we got, just let's imagine that the total value we got here is 5. And the total value we got here is, I don't know, minus 2. So the total force would be the square root of 25 plus 4. And that would give you you would do this calculation, right? JC, you would do the
Right.
29. Okay. That would be the total force. But you want, that would be this total force that's going here, this one. But you need to know in what angle that force is going, okay? So how do you calculate the angle? Once you have these two values of fx and fy, you do this. The angle is going to be the inverse tangent of the x value, which in this case is -2. I'm sorry, the y value, which in this case is -2, divided by the x value, which is 5.
Okay, so that's how we get the direction of magnitude.
Correct. So it's the magnitude is always going to be the x force and the y force with the Pythagorean, using Pythagoras, and the angle is always going to be y divided by x, inverse tangent. Okay, questions with this one?
Oh, I got it. Like I had a refreshment of physics right now.
Yeah, and the other thing, but something we haven't addressed yet. This is just this was just a kind of like a crash course in free body diagrams that we're doing. But we haven't addressed the other doubts you have that, well, how do I know where the forces are going? Because of the charges and all that. So let's talk about that next. Questions with this before I clear it. Remember that all this is being recorded. So you're going to have this in the recording and you can go through it again. Can I clear this right now?
Yes.
Okay, so I'm going to clear in 3, 2, 1. Now let's do the following. Let's forget about a ball on the floor and let's start talking about charges. Let's say that I have a negative charge here. And let's say that I've got another negative charge here. And I've got another negative charge here. These two are separated by a certain distance. I'm going to call this R. And these two are also separated by the same distance, R. Okay? And I'm going to say that we've got an angle here of 60 degrees. Okay? Are we okay up to that point? I'm just putting 3 charges in space. Okay? I want to know what is the total force that's being exerted on this charge. Or in other words, I want to know that charge, is there a force in that charge? And if that force, where is it trying to move the charge? Why would there be a force? If I put any charged object, the charged object is going to generate an electric field. The electric field by itself isn't going to do anything. But the moment I put another charged object in the electric field, that's when things start to happen. Okay? So, are we okay up to this point with the situation here? That we've got
Yes.
here?
Yes.
Okay. We're going to take the 10-minute break and we will return with this problem. I'm not gonna stop sharing the screen, so we've got so we can continue with this. Okay, so I'm going to pause the recording and we're going to do the 10-minute break. Okay, so again, we're looking at the free body diagram here of this situation. We've got 3 charges. Let's assume also, for the purpose of the problem, let's assume that the 3 charges have the same value of charge. Q. They have the same value of charge. Okay. And we want to know the total force that's being exerted on this charge here that's on the bottom right. Okay. Remember, any questions, please stop me. And so I'm going to do a free body diagram here to try and to analyze the situation. And so let's see. I'm looking at this charge here, this one. We're doing the analysis here in this one. Okay, so let's see, Rene, let's go through this a little bit. So I'm trying to remember what we saw before. So I'm here in this charge Q. And I've got another charge Q over here. And both of them are separated a distance R. First off, since they're separated a distance R, I'm just looking at this one, which is Q, the ones that are on the horizontal plane. I'm just looking at this one and at this one right now. If both charges are the same, then what type of force is going to be exerted among them? Is it going to be an attraction or a repulsion force?
Repulsion.
It's going to be repulsion. Okay. And so if it's a repulsion force, between those two, in what direction is this charge here, the one on the right, in what direction is it going to be pushed or trying to move?
Professor, sorry for interrupting your conversation with Amar, but if they're all negative, isn't it attraction? Negative attract, no?
No. That's the basic principle of Coulomb's law. And again, something very important, Jose Carlos, that you mentioned, that please, everybody, try to focus when you're doing these problems or these analysis. Let's try to do a systems approach. And that means that we're going to separate things into different parts and not look at everything at the same time. Right now, Jose Carlos, I'm just talking about this charge and this charge. Forget about the rest of them. Right now, I'm just talking about those two.
Okay.
Okay.
It's because I stopped to because it was like the basis of something that I knew, and then I didn't know if I had it right or wrong, because I'm pretty sure that if it's positive and negative, well, the energy goes to the negative, right? No, the negative attracts the.
Uh-huh.
But if there are two negatives, it's repulsive.
Mm-hmm.
Because they both are trying to attract the energy, or what happens? Or right,
No,
right now that let's not get into that because it's not that important.
No. It's hugely important because that's the basis of everything, and it's basically the rule here is positives attract each other. I'm sorry, opposites attract each other. That's going to be the rule. The ones that are the same are going to repulse each other. That's going to be the rule, always. Opposites are going to attract, and charges of the same size are always going to repulse each other. And that's basically because of what we saw about the electrical fields. So what's happening here with the electrical fields is that I'm going to draw, remember, Jose Carlos, the electrical field, which is basically this energy that's being emanated by a charge. The electrical field of a negative charge, how did we represent it? Did we represent it as going inwards or going outwards?
The electric field of the negative charge.
Mm-hmm. Remember, we did these diagrams.
It goes in, or no?
It goes inward. So this electrical charge has an electrical field that's going like this. Okay.
Mm-hmm. Yes.
That's the electrical field of that charge. Well, this is a negative charge also. Okay. So the electrical field of this one is also going to be going like this. Do you notice that the electrical fields are opposing each other?
Yes.
So that opposition generates the repulsion, always. Okay.
Okay. Thank you.
Is that so? Is this part clear up to this point?
Yes.
Okay, good. So now, if I've got these two charges, then the electric force that's being generated between these two is going to be a repulsion force. And if it's a repulsion force, it means it's going outwards. So I'm going to have a force here that if this is, I'm going to call this charge 1, charge 2, and charge 3. This force is going to be the force between charges 1 and 2. Okay? Are we okay up to that point? Questions up to this point?
No, I'm good.
No questions.
Okay. Now let's look at the other two charges. So now we've got Q3 and Q2. These two are also along the same line. And so these are also both negative. And since they're both negative, there's going to be a repulsion between them. Okay? And that repulsion force is going to go along this line. And I'm going to call that force F32. Okay? We're okay up to this point? This is the part that you were asking about, Rene, that's also important, that might be generating confusion, but it's also important to clear up, is the direction of the forces. How do we know where the force is going? Well, we need to identify if it's a repulsion or an attraction force. And we're always going to be seeing that between two things. So that's why I was mentioning when Jose Carlos was saying, well, what's the effect of all of the forces? Well, we're going to get to that when we solve the problem. But right now, we're just looking between A and B, what's happening. Then between B and C, what's happening. We're seeing those separately. So are these two forces clear to everybody?
Yes, but what happens with the other way that they are going, the forces, the arrows? What happens with them?
Which other arrows? I'm sorry,
The ones that are with Q3 and Q1. The other way that the force goes, because they repulse each other.
I understand. I think I understand. You mean, I'm going to mark them. You mean these?
Yes.
Oh, very good question, Alex. I don't care about those right now because where is the free body diagram right now?
Okay, we're getting focused on the other side.
Yes, right now it's a very good question, Alex, and I'm glad you asked it because maybe that's also generating confusion. There are other forces acting on the other two charges.
Mm-hmm.
We're going to analyze those also, but right now, where am I? I'm in Q2. So I'm only looking at that. So that's why the free body diagram is important and where you put the free body diagram. Right now, I'm only looking at what's happening with this charge. Okay? Is that clear, Alex?
Yes, thank you.
Okay, additional questions. Okay. Now this force F32 that's going downwards has an angle. What angle is that? What angle does this force have here?
60.
60 degrees. Okay. Now we want to find the total force that's being exerted here. So the total force is going to be given by two components. It's going to have an X component. And it's also going to have a Y component. And I need to find those. Now the X component is going to be the sum of all of the forces that are acting along the X-axis. Okay. Can somebody tell me what are the forces that are acting along the X-axis, please?
The F12, the F32,
Mm-hmm.
and you have the well, that's the one you have illustrated, but you have the other ones, no, the other charges, but we haven't seen those yet.
Yeah, but again, and again, it's important you comment that, because I'm going to go back to what I mentioned to Alex. We're just looking at the free body diagram that's here. We're going to be looking at the other charges separately, but right now we're just looking at the things that are here in the free body diagram. So what are the forces there? You've identified one, which is F12. And also F32 has an X component, but how is that X component represented?
So you're going to have F32
cosine of 60.
sine cosine
Correct.
of 60.
Correct. F32 cosine of 60. Okay. And then we've got the force. We've got the force in Y. The force in Y is going to be equal to the sum of all of the forces in Y. What are the forces in Y that are acting here in this diagram?
Just
Or the forces?
just the purple 32, F32. Negative.
F
And it's
negative, correct. And but the
FY.
that's F32 and the Y component of F32. And how would we calculate the Y component of F32?
The sine of 60.
Sine of 60. Okay. Questions up to this point before we start going into the calculations?
No question.
Okay. But what are the values of F12 and F32? Well, this is where we go to Coulomb's law. So F12 is going to be K multiplied by Q1 multiplied by Q2 divided by R squared. And we know that we know these values. R is 0.2 meters, right? 0.2. And the charges we had mentioned are 4 times 10 to the minus 6 coulombs. Okay. And we know that K is a constant. Okay. So if we do these calculations, force 1, 2, if I'm not mistaken, can somebody refresh our calculations there? That force we had gotten that it was 3.59, right? Please, just to refresh, do the calculations,
Yes.
please. Thank you. 3.59 newtons. And then yes, go ahead, Alex.
Does the Q's have the same value?
Yes.
Or they're different?
Yes, all of the charges for the problem of the triangle, all of them have the same value.
Okay, thank you.
And F32 so just to be clear here, Q1 is equal to Q2 and is equal to Q3. And so F32 would actually be the same value because the charges are the same. So it's going to be K, Q2, Q3, R squared. And this is going to be exactly the same value because the values are the same. So this is also going to be 3.59. Okay. Are we okay up to this point? Questions up to this point? The only thing we're doing is using Coulomb's law to calculate those values. And now if we substitute these values into this expression here, F12 plus F32 cosine of 60, we had also already gotten those values. And I think f of x, and please try to do them just so you can review them, was 5.38. And the sum of forces in y was, I think, minus 3.1. Can you guys please verify the values, please? Can somebody tell me the value of Fy in this calculation, please? Please, somebody.
Y
Mhm.
is
3.10?
negative.
Negative 3.10?
Correct. I thought I remembered it was 3.1 or
3.11.
something. I'm going to say 3.1 newtons. Oops, it's a large n. Okay. And now the last thing we need to do is to do the calculation of the total force. And the total force we mentioned was going to be calculated by the Pythagorean theorem, which is Fx squared plus Fy squared. And if I'm not mistaken, this is 6.2 newtons, right?
Yes.
And the angle of this force is going to be the inverse tangent. And remember that if you're going to be doing calculations with trigonometric functions, remember to have these in degrees. Tangent is going to be of Fy divided by Fx. And this is going to be, I think, roughly, I think it's minus 29.9 degrees. Okay. Now that means, and I'm just going to mark it here in red, that the total force Ft and the angle theta, Ft is going to be going, then the total force is going to be going roughly something like this. It's going to be a total force going in this direction. And the angle is going to be theta here. Okay, which is going to be this minus 29.9. Now, notice that in the answer, it says 150 degrees, right? Why does the answer say 150 degrees instead of 29.9 negative, and both are correct? Can somebody tell
They
me?
just subtract the 180?
Because the angle that I'm measuring it's negative 29.9. That means that the angle is going from the negative axis to the force. That's why it's negative 29.9. If I were to measure the angle with regards to the x-axis in a positive direction, it would have to go like this. And this angle is 180 degrees minus theta, absolute value. So both answers are correct, actually. Okay. Now, questions with this one. This is, again, it's important for this problem to be clear, because a lot of the other problems are going to be also, we're going to be doing a few problems that have these characteristics. So questions with this one?
The professor.
Yes, go ahead, Alejandro.
So all the calculations we made is for the forces of the three charges, or only for the charge 2?
Only for the charge 2. Right now, we're just looking at charge 2, because actually the problem says to identify the forces in each charge. And we're going to talk about the other 2 charges in a minute. But right now, remember, we do the free body diagram in the place where we are looking where we're doing the analysis. Okay. So right now, we're just focusing on Q2.
Okay.
Okay. Questions, additional questions?
No.
Okay. Okay, so if this is clear, then what we're going to do is the following, okay? I'm going to give you a couple of minutes, and for you guys to do this individually. I'm going to give you a couple of minutes to try to do the same thing, but with Q1 and Q2, okay? I'm going to give you 5 minutes to do in your notebooks or whatever, 5 minutes to just do the free body diagrams in Q1 and Q3. So one is the free body diagram in Q1 and the other is the free body diagram in Q3. I want to see if you guys are understanding how to do those. And then we're going to come back and do them here. So just do the free body diagram and identify the forces, okay? 5 minutes. Now, is it okay for everybody if I erase some things from this diagram? From this slide?
It's fine for me.
Okay, if take
Professor.
yes, go ahead.
We got the negative 29.9, right? And you subtracted it from the 180. How was that? I didn't get the last angle.
Oh, okay. So first off, Jose Carlos, the negative 29.9 is a correct answer.
Okay.
Okay, so you can leave it like that.
But we can write it, okay, a different way.
Yeah. Remember that when we were talking about angles, so a positive angle means that I'm measuring it counterclockwise with regards to the x-axis. Okay. A negative angle means that I'm measuring it clockwise. So if I get negative 29.9, it means it's this red angle that I marked here. Do you see that, Jose Carlos?
Yes.
Because it's going counterclockwise. Okay. But if I don't want to represent that as a negative, just because, and in the answer they represented it as a positive angle, it means I would need the angle that's counterclockwise. And what's the angle that's counterclockwise? It's the complementary angle of theta, which would be 180 minus theta, which in this case is 150 degrees.
So wouldn't it be also 360 minus? No, I thought it was going to be 360 minus 29.9. No.
It would. Oh, the thing is, that's confusing. I'm sorry about this. I marked it.
Because 180 is half, right? So if it's 90, 180, 270, and then the angle it's more than 270, no?
it would be, give me a moment. Actually, yes, actually you're correct. If we were looking at the angle, give me a moment.
It would be.
It's actually correct. If we were to be
331.
looking at, yeah, it would be, it would be 330, and only if we wanted to represent it as an angle that's less than 180, that's when we would use the 150. So the 331 or the 150 or the minus 29.9, all of those would be correct.
Okay.
As long as you're referencing them in the diagram.
Okay. So the final answer would be the 6.2 at the angle that we found.
Yep. Mm-hmm.
And that is what we found right here is the force at this point, the point in the middle.
In the Q2. Correct.
Okay.
It's the total force that's being exerted on Q2, product of all of the rest of the forces that are acting there. Okay. And that's because this is where we're doing the free body diagram.
That happened to me here and in the past class, that I understand every step you're making, but then like I don't find the purpose in that when you ask me to do it, like I don't know where to start, but I understand everything you're doing. Like right now you told us to do the force stressed on Q1 or Q3 or both? Both. Okay.
So let's go with that, Jose Carlos, because this is weird, and I don't know if this has to do with the Zoom education or not, because I don't know if this would be happening in a normal classroom. But exactly the same thing. That's why I'm trying to go slow here. Exactly the same thing I noticed last semester when I was teaching the electronics course. So I was doing a bunch of examples, and I was actually doing videos and doing a bunch of examples and asking everybody if everything was clear. The problem was when I asked them or I gave them some homework tasks, that's when the problem started, okay? Because so it seemed to be clear, but when you guys tried to do it, or the students tried to do it, that's when the problems came up. So let's start off with, let's try to do the free body diagrams, which would be the first step. Let's try to do that with Q1, okay? And help me out here, JC, okay?
Yes.
We all know the values, so I'm just gonna erase this just to make it a little bit cleaner here, okay? Because I'm interested in the free body diagram because that's the important part. So we already did the free body diagram for Q2. Now let's see what's happening with Q1, okay? So first thing, I'm gonna do the free body diagram. Okay. And now for this analysis, remember, I'm only looking at Q1, okay? I'm only looking at Q1 and what's happening in Q1, okay? Now, JC.
Yes.
I'm hearing Q1 and there are two charges here. There's a charge Q2 and there's a charge Q3 that we've got there, okay? And so if I'm hearing Q1, there's a force between Q1 and Q2. Would you agree with that?
Yes.
Now, what type of force is that?
Repulsive.
Repulsion, correct. So if it's a repulsion force, where would the force be going if I'm placed here in Q1?
To the left.
To the left, correct. And would you agree that it's to the left along the x-axis?
Yes.
Okay, perfect. So are we okay up to that point?
I am.
Perfect. So it's F, I'm gonna call this F12. By the way, it's exactly this same force that we had over here on the other diagram.
Yeah.
Okay, it's exactly the same force. That's why when you were at when you and Alex and both Alex actually Alex and Alejandro asked, well, but what happens with the rest of the forces? Well, the forces are still there, but we're looking at different views of them. Okay. Now, would you agree that there's a force between Q1 and Q3?
Well, it's not written down, but yes, I guess.
Well, let's remove the I guess. Remember that if there are charges placed anywhere, number one, there's going to be electric fields, and if there's electric fields interacting, there has to be a force. Okay. What magnitude that force is or where it's going, we don't know, but there's going to be a force.
So now we're gonna join Q2, Q1, and Q3.
So now let's look at Q1 and Q3. Q1 and Q3. No, we're still looking and we're hearing Q1. Okay. What is the force between Q1 and Q3 if I'm hearing Q1? Alex, is it a repulsion or an attraction force?
A repulsion.
Repulsion. In what direction would that force be going, roughly? And if you want to draw it there, you can, or just mention.
Down to the left.
Perfect. You can actually just say that, down and to the left. It's going to be going down and to the left. And I'm going to call that F13. F31. Okay. Now, this is an equilateral triangle, so this is 60 degrees. This is also 60 degrees. So what would be the angle of that force? Of 60. This force here?
60.
60 with regards to x, okay? Are we okay up to that point? So
yes.
Questions with the free body diagram. Is the free body diagram clear? Everybody?
Yes.
Yes.
Exactly the same thing is going to happen. F12 here in this case is exactly the same force that we had calculated before here. And you guys already have the value of that. It was 3.59, right? Remember? It's exactly the same force in magnitude. It's going the other way, but in magnitude, it's the same. And would you agree that the force 3.1 has to be the same value?
Yes.
Right? Why is it the same value?
Because it's the same direction.
It has the same, the charges are the same, the distance is the same.
Professor, I was going to ask you that too. When would it not be equal? When the charges are different? Like right now, we don't know the exact charge of the circles, no? Or do we?
It's the same problem, Jose Carlos. We haven't changed it.
I know, but this circle, the blue circles, Q1, Q2, Q3.
It's the same problem. We had mentioned, remember, Jose Carlos?
We did that they have certain charges.
Yes, Jose Carlos. It's important to please. I'm sorry about that, but we do have to be paying attention. We mentioned that it's the same problem. We haven't changed problems, and we wrote this down many times. Q1 is the same as Q2, is the same as Q3, and the value.
You wrote it on the bottom left corner. I saw it. Oh, -4. I didn't see the -4.
Yeah, all of them have the same values. They have the same values. Now, it's correct, before I go to Alex's question, it's correct what you mentioned, Jose Carlos. When are the forces going to be different if there were a situation where the charges were different and the distances were different? Right now, for this situation in particular, the charges are the same and the distances are the same. So it's given that the forces are going to be the same also. And that simplifies calculations. Okay. Yes, Alex, go ahead.
So it wouldn't, the force 12 wouldn't be negative if it's going to the other way of the x-axis.
Oh, yes. No, you're correct, Alex. But right now, I'm just writing down the magnitude here. In the 3.59 is just the magnitude. I'm not indicating the direction. I'm going to indicate the direction in the next step, which is when we're going to be calculating the forces in x. This is going to be the sum of the forces in x.
Thank you.
And this is where what you're commenting is correct. What are we going to have here, Alex? We're going to have negative F12 and negative F31 cosine of 60. And then Fy, give me just one moment here. Fy is going to be Fy is going to be the y component, which is going to be minus F31 sine of 60 degrees. Okay. And actually, these two are going to be the same values. If you notice, since we have the same values, it's going to be the same values that we calculated in the previous problem, just that we're going to have different signs. This one, if somebody can help me out with the values, this was, I remember that Fy
was negative 3.1.
Negative 3.1, correct. Thank you, JC. I remember that one by memory. And Fx, what value did we have there?
5.38.
5.38. And the only difference now is that it's going to be negative because it's going to the other side. And the total force is going to be also, actually, it's going to be a force that's going to be going something like this. The total force is actually also going to be calculated the same way we did with the other one, which is the square root of Fx squared plus Fy squared. And this is going to give us 6.2. It's the same 6.2. And the angle that we're going to have here we should get also something here. The angle, in this case, it's going to be the inverse tangent also. Just that we have different signs there, so the angle might have a different sign also, but it's going to be congruent of Fy divided by Fx. And I think that this one is I think that this one should also give us 30, right? Can somebody do the calculation, please? It's either going to give us 20, also the 29.9, or it's going to give us I think it's going to give us 29.9.
29.9, yes.
Yeah, but it's going to be positive because I'm measuring it clockwise, counterclockwise. I'm sorry. And so now we notice that we were looking at Q2 and we had the resultant force. But then when we go to Q1, which is the same, but on the other side, we have the same forces, but but in the other direction. And why are they the same forces? Because the charges are the same and the distance is the same. So the overall effect that we have on Q2 is going to be the exact same effect that we have in Q1. And that makes sense because systems have to have equilibrium. Okay. Now, questions here before we go to the last one?
No.
No questions.
Okay. Can I erase some of this? So you guys taking screenshots? Or it's going to be recorded, but if you want to take a screenshot, I'm going to erase some of these things. Let me just write down this here.
I'm okay.
Okay. Okay, and this is the force here. Now, I'm gonna not erase everything, just a few things here. Okay, so now let's look at Q2. And so let's look at Q2 and let's do the free body diagram in Q2 and let's see what's happening there. And so in Q2, I'm going to do the free body diagram here. Put this here, put this here, here, and here. Now we're just looking at Q3. Is it clear that there's a force between Q1 and Q3? Can somebody tell me what type of force it is and in what direction it would be going?
Repulsive, and it's going northeast.
Oh, perfect. I like that. It's easier if you don't want to draw. It's easier to represent it either northeast or up right. So it's basically very, very well done, JC. It's going like this. It's a repulsion force between F1 and 3. And what is the there is a force between Q3 and Q2. And can somebody tell me what type of force that is and where is it going? In what direction?
Northwest.
Northwest.
Repulsive.
Repulsive, and it's going like the son of Kanye and Kim. He's called Northwest, right? Why would somebody call their child?
I think, yes, Northwest, yes, it's called North.
Yes.
Right?
I mean, why would people do that? But I mean, just my wife and I were this close to calling our daughter Sarah Ray Sosa Aguilar, because the first Star Wars movie, The Force Awakens, had come out and we were kind of fans of Ray. And we were this close to calling her Sarah Ray, and we decided against it and called her Sarah Michelle. And now we're glad we didn't make that decision because we became non-fans of her after the next 2 movies. So it's going northwest this way. Now, can somebody tell me what are the angles that we have here?
Both are 60, right? With regarding the X.
Both are going to be 60 because we're going to have the complementary angle here actually is also going to be 60 degrees. So this is going to be 60.
Professor,
should be 60.
No, it's supposed to be 30, no? I think.
Wait a minute. Let me let's see.
I'm not sure, but
we've got 60 degrees here. That means that this angle here is 30 degrees. Okay. This angle here is 30 degrees. Are we okay? And this angle here is a right angle. Okay.
Oh, okay.
So this angle here also has to be 60 degrees. That's good to verify because again, with the fuzzy brain, and sometimes we so yeah, that would be, I'll leave that there.
Professor.
Go ahead, Casey.
It's a triangle, right? No, okay. You're right. I'm wrong. I thought I saw it differently, but no, it makes sense.
Oh, yeah, it's sometimes it's just because we're kind of rotating the axis here, and this would also be 60 degrees.
Professor.
Yes.
Why don't you rotate your free diagram?
We could do that.
X-axis and Y-axis.
That's a perfect. That's a very good observation, Pedro. We could actually do that also, and that would make things easier. Actually, it would make things very easier. We could have also done, and I'm doing it this way purposefully just so we can see the difference, but we could have also put the free body diagram like this. And that would have been a very direct calculation. If you do that, it's correct, okay? And you're gonna get to the same result, okay? But yes, we could do that also. I'm not gonna do it right now because I'm gonna have to redraw everything. But yes, that would be correct. And now let's see what's happening here. The sum of the forces in X, would you agree it's gonna be F13, whoops. Cosine of 60 degrees minus F23 cosine
Professor,
of 60 degrees. Yes, go ahead, Jason.
I think I don't know if I'm wrong, but I'm seeing the drawing right now, and in your white sketches, it's a perfect 90-degree angle, right?
It's trying.
But
it's trying to be a
like
perfect degree
the
angle.
30 the 30 that we wrote on top, it touches the white line and the yellow line, right?
Oh, yes.
So
Wait a
the
minute.
60 the 60 would be from the yellow line to the white line.
You are not incorrect, JC. You are not incorrect. And I was wrong here. This is right. Yes. Good. Thank you, JC. And you are right. You are right. Yep. So this angle here, actually, this angle here is 30 degrees. This is the one that's 30 degrees with regards to
but I think it still makes it's still 60, right? The one we're using.
Let me just check that, because again, I got fuzzy brain and I don't want us to do a calculation that's incorrect. This is 30. And I just wanted us to demonstrate whatever we need to demonstrate. This is 30. That means that this is 60. Okay. And that would make this 30. Correct. That's a good observation here. I made a mistake. So it would be cosine of 30. Okay.
It will still be 60, no?
Yes, it is 60.
It's just a mirror.
It is?
Yes, like the free body diagrams that we did.
Let's just verify that, because we're getting, I want us to get
I think because if you rotated the purples to the white lines, wouldn't it be still the 60? Because it's not at 90 degrees
Professor.
inside, so if you rotate it, it's a 60.
Yeah, I already saw it.
Yeah, it is. Yeah, you're right.
I'm sorry, I made so much confusion, but like it didn't.
No, actually, I'm glad about it, JC, because at least we're paying attention. At least if I make a mistake, we're or if anybody makes a mistake and we review it, we kind of understand where we're going. So yeah, so it would be 60, right?
Yeah.
Right.
Correct. Okay, so it's 60, and it would be F13 cosine of 60 minus F23 cosine of 60, and F13 and F23 are going to be exactly the same values that we calculated before, and these values are the same. And so what's going to happen, and we can actually see that in the diagram, the two forces are going to, the X forces are going to cancel each other out. So the total X force is going to be 0 degrees. Okay. And in this case, Fy would be the Y components, which is going to be the sum of F13 sine of 60 plus F23, yeah, 23 of, and the sine of 60. Okay, and this should give us, if I'm not mistaken, can somebody do that calculation, please? This should give us the 6.2,
6.2,
right? Yeah. 6.2 newtons, because sine of 60 is 0.5, and plus sine of 60 is going to give us 0.5 plus 1 multiplied by that. Ft then is going to be the same way we calculated, the square root of fx squared plus fy squared And this is going to be actually, since we don't have an Fx, it's going to be the 6.2, which is exactly the same force that we had calculated before, but now it's going to be going directly upwards. The angle in this case, we're going to have a force Ft that's going to be going this way. It's just going to be an X. The angle, which would also be calculated the same way, the square root, I'm sorry, the inverse tangent of Fy divided by Fx. And in this case, Fx is 0. So it would be the inverse tangent of infinite, and the inverse tangent of infinite, well, this would be 90 degrees, which is congruent with the with what we're seeing in the diagram here. This would be this angle here. Okay. So notice.
Because,
yes, go ahead.
I have a question. So because it's everything is the same, we in the end we end up with the same force, right? With the
Yes.
same total force.
Correct.
The only thing that changes would be the angles.
The only thing that changes is that depending on in which charge you're located, in what direction the forces go. But what I was going to get at, so spoilers, what I was going to get at when everybody was asking what happens with the rest of the charges, the net force has to be the same. Because again, this is physics. This is normal physics, not any other types of physics. The net force has to be the same, but the direction in which it's going, depending on where we're located. Okay. Okay. So we're gonna leave it here. We're gonna continue with the rest of the problems on Monday, and I'm gonna upload these. I'm gonna upload these recordings so you guys have them and are able to have access to them.